Okay, starting topic 3. This is chapter 2. The first main idea is uniform motion, meaning motion that's in a straight line at a constant speed. And so the motion diagram will be a series of dots equally spaced, all in a line. Wouldn't have to be a horizontal line, could be some angle. Maybe this is something moving down maybe this is somebody going down an escalator, for example, or going up an escalator. You can't really tell unless we put the velocity vectors in there. And then for this type of motion, uniform motion, the position versus time graph will be a straight line. It might be increasing position as time goes along, or it might be decreasing position along the x-axis as time goes along. But either way, it's going to be a straight line. So the average velocity will be the slope of the graph. It'll be the rise over the run, the change in x over the change in t. And by the way, this symbol here, the triple equal sign, means a definition. So this is the definition of average velocity. It's different from saying that this thing is equal to this thing. It's saying that this thing is defined as being this thing. So the point of uniform motion is that you could look at any particular delta t, any particular time interval that you are interested in, and you're always going to get the same average velocity. So just as an example of that, here's some uniform motion depicted on an x versus t graph. And if we look at an interval of time 0 to time 3, the change in x here is 4, the final x, minus 3, the initial x. That difference is 1. And then the delta t is 3, the final t, minus 0, the initial t. And that difference is 3. And so our v average would be delta x over delta t, which is 1/3. And if we have meters and seconds as our units, the average velocity is 1/3 of a meter per second. On the other hand, if we look at this interval from t equals 3 to t equals 9, we would have a delta x of 2, 6 minus 4, and we'd have a delta t of 9 minus 3. 9 minus 3 is 6, and our average velocity there is positive 2 divided by 6, or the same thing, 1/3 meters per second. So no matter where you look at the motion, you're going to see the same velocity. It is important to understand that the average velocity is not x over t. Delta x over delta t is not the same as x over t. As an example of that, if we look at the t equals 9 instant, at that instant x equals 6, and if we were to take x over t, we would get 6 over 9, which is 2/3. That's not the correct average velocity. So it does not work to say that the average velocity is x over t. You have to have a difference. And the reason it doesn't work is because this is offset from the origin. The line doesn't go through the origin. If that line happened to go through the origin, this actually would work, but that generally isn't the case. Okay, so in uniform motion, at any instant, the velocity is always going to be the same average velocity. And so we would have v at any instant would be delta x over delta t. And if we solve this for delta x, we just multiply through both sides by delta t. We get v delta t on one side, and the delta t cancels on the other side, and so delta x equals v times delta t. In other words, our displacement is equal to our velocity multiplied by the time interval. And this velocity could be positive or negative, depending on the slope of that x versus t graph. And then the displacement would have the same sign as the velocity. Of course, the time interval is always going to be positive. And continuing on with this, the delta x is actually the final x minus the initial x, or we could say x2 minus x1. And then if we solve that for x2, how do we do that? We add x1 to both sides, and so x2 is equal to x1 plus v delta t. So now this tells me, if I know where I started, and I know how fast I was going, with including the sign here in the velocity, and I know how long I went, then I'll be able to know where I ended up at the end of that time interval. This is used in question 1 on practice exam 1. But it's important to understand this formula only works for uniform motion where the v is a constant throughout the motion. There's another example of this, a nice example in the book, example 2.2 called Lunch in Cleveland. It's 2 people starting in different places and then planning to meet for lunch, and they're going at different speeds, and the question is, where do they meet? So it's kind of related, covers the same concepts as this question 1 on practice exam 1. Good example. I encourage you to read that. Okay, as a lead in to the next topic, where we're going to be dealing with velocity that isn't constant, motion that isn't uniform, I'm going to look at motion that is uniform over some range, but then there's different ranges where we have different velocities. So in this range from 0 to t1, here in this example, we have uniform motion. But then this object actually stops, right? As time goes from t1 to t2, its position doesn't change. So it stopped. And then it starts moving in the negative direction more rapidly than it went in the positive direction at the beginning. In each of these intervals, the motion is uniform, but it's not uniform overall. And if we were to make a velocity versus time graph, this is the main topic of the next section. We haven't seen this before, but if we were to make a velocity versus time graph, we would be showing what is the velocity during these different time intervals. And the velocity during this interval, from 0 to t1, we would get from the rise over the run, the slope of this part of the graph. And that's a positive slope, so it's a positive velocity. In this interval, the slope is 0, and so the velocity is 0. And that makes sense because the object wasn't moving. We already knew that. The object isn't moving here. Its velocity is 0. And then in the last interval, the velocity is negative. The particle is moving in the negative x direction. And it's a steeper slope, so it's a larger negative value compared to the positive value that it started with. So this is the velocity versus time graph for this same position versus time graph. So these are related. They don't have exactly the same information in them, but they do cover a lot of the same information. Okay, and that leads into this idea of instantaneous velocity. So if the motion is not uniform, then we're going to have different velocities at each instant. And if we pick 2 different time points for our interval, we're going to get a different average velocity each time. So here's an example. This is a motion diagram of something that starts at a positive x coordinate and then moves, starts slowly and moves faster in the negative x direction. These really should be all along the same line, but I kind of spread them out just so the dots aren't overlapping each other. It moves to a negative x coordinate, then it stops, starts moving in the positive x direction, speeds up, and then continues on. And here is the x versus t graph of that same motion. It starts positive, goes negative, stops momentarily, and then starts going back in the positive direction. So if we were to pick 2 points here, t1 and t2, and consider the average velocity between those 2 points, we can see that the velocity, the slope of this line, does not exactly match the slope of the curve, the x versus t curve here, at any particular instant. And if I zoom in on that part of the graph, this shows that the slope, so at this point right here, the slope is this dashed line, and it's not the same slope as the average velocity. That's a consequence of this being non-uniform motion. So how can we get a more accurate velocity? Well, the answer is going to be to take a shorter time interval. But before I talk about that, I want to point out that in physics, we don't always want to be more accurate. We only want to be as accurate as we need to be for the problem that we're trying to solve. We don't want to make it harder than it has to be. And that may be counterintuitive as a physics student. You might think everything's harder than it needs to be, but that's because you're learning it. But if if you're really using physics to solve problems, you want to use the simplest model that you can. So if you can get away with assuming constant velocity, then you would want to do that. But in this case, we can't. We're saying that we want more detail, we want more information than this straight line. We want to capture some of this curve here. So how do we get more accurate? Look at a shorter time interval. So here's my old delta t, covers this whole width of this one little segment of the graph. But I'm going to look at a new shorter delta t. And in that shorter delta t, I can see that my average velocity, the straight line here, is going to be a lot closer to the curved, the slope of the curved line at any point. Still not exact, but it's going to be closer. So there's a pretty small difference between average velocity and velocity over this time interval. Okay, so you're probably seeing where I'm going to go with this. If I want to be even more accurate, I'll take the limit as my time interval gets infinitesimally small. So delta t goes to 0. And that's going to give me the instantaneous velocity. So my velocity at some instant t is going to be the limit as delta t goes to 0 of the delta x, the rise, divided by the delta t, the run. But x is a function of time. So the delta x will be the difference between the position at t plus delta t. So this is t here. I'm going to call this t. I may have gone off the screen here. I'm calling this t. And this is t plus delta t. So I take my x coordinate at t plus delta t. I subtract my x coordinate at t. And that is my delta x. And my delta t is just delta t. And we're taking the limit as that goes to 0. Well, if you were paying attention in the first part of calculus, you would have seen this kind of thing here. And this is exactly the definition of a derivative in calculus. So this is what we would call dx dt. So the velocity at any instant in time is the derivative of the position. It's dx dt. Another way to put that is that the velocity is the slope of the function of the graph, x of t. Now, in calculus, you're probably used to thinking of derivatives as dy dx. This is where y was some function of x, and you have a very similar looking formula here. In fact, it's exactly the same formula. All we have to do is replace y with x. So everywhere you see a y, replace that with x. Everywhere you see an x, replace that with t. And now you have the derivative dx dt. So in physics, the independent variable is usually time, and the dependent variable might be anything else. But in this case, it's going to be position. So it's worth your time to look at example 2.3 and 2.4 in the book. Example 2.3 has a couple of figures that are really going to take you some time to process and make sense of. It's worth spending a few minutes on that. And these examples are both on page 38 and 39 in the book, and in the e-text, those page numbers are in the left margin if you're trying to find those quickly. Okay, I'm going to press on here. So we know how to find the velocity now if we're given a function of position as a function of time. We would just take a derivative. V is going to be dx dt. We'd use our calculus skills, whatever function this is, if it's x squared or e to the x or whatever, we would take a derivative and that would give us the velocity. What if we're given the velocity and we want to find the position at some time? So here's a graph of velocity. We have a particle here that's moving in the positive direction because the velocity is positive. It's above the axis here. And then its velocity becomes less and less positive. In fact, right here, the particle instantaneously stops. Its velocity is 0 at that point. And then it starts moving in the negative direction. And then it is still moving in the negative direction, but very slowly by the end of this motion. So the problem here that you might be asked is to find the displacement over this time interval from t1 to t2. So what is the delta x? Well, there's no x in here. All we're given is v. How are we going to find x? Well, if the motion was uniform, we would know how to do that because we already derived this. Delta x is v times delta t. That works if v is a constant. But here we have non-uniform motion. Clearly v is not a constant. It's all over the place. So the trick is to split our interval into a bunch of little steps. So tiny little delta t's. And we split our interval into a bunch of those little delta t's. They're all equal. And during each of those steps, we can say that the velocity is more or less constant. We know it's changing, but it doesn't change by a lot during one of these given steps. It only changes by a little bit. So we'll get a pretty close answer if we say that it's a constant velocity during one of these steps. Now for each one of those steps, if we're saying that the velocity is constant during that step, so the first step, the velocity is, say, v1, we could call that velocity v1. Our delta x for that particular step would be v1 times our delta t. In other words, that's the length of this rectangle times the width of it. That's the area of one of these skinny rectangles. For the second step, we'd have a different delta x. It would be the v of that step, v2, times the same delta t. A little bit shorter rectangle, same width, so a little bit less area. Now, if we want to know the delta x over the entire interval from t1 to t2, we have to add up all our little delta x1, delta x2, and so forth, all the way up to the last one. And of course, each one of these delta x's being an area, what we're getting is we're getting the total area of all the rectangles. Now we do have to be a little careful here because when the v is negative, we're going to have an area that we have to subtract instead of adding. So our delta x in these intervals would actually be negative delta x's. We're still going to add them, but they're negative values. And if you were paying attention in calculus, you may see where I'm going with this. An even better idea would be to take the limit as the step size goes to 0. The delta t's become small. And if we do that, we're going to get an integral. You already saw I was adding up to get the area under the curve, right? Well, that's what the integral is. And so in this case, our delta x would be our sum becomes an integral. In fact, the reason the integral sign looks like an S is because it is a sum. It's a sum of these little tiny rectangles. They're infinitesimally skinny rectangles. And because they're so skinny, the v doesn't change much within one time interval, within one time step. And so this all works. So we're going to take, instead of having just a v times a delta t and adding them, we have an integral of a v times a dt, where dt is the infinitesimally small delta t. Now v is going to be some function of t. If you go back and look at this curve, I don't know what function this is. It sort of looks like it might be a cosine or something, but then it sort of fades out. So it's some complicated function, but it is some function of t that we could express mathematically. You know, t squared plus 3 or t times e to the minus t or something like that. So that's how we would actually integrate it using our calculus techniques that we learned in Calculus 1 or Calc 2. There's some good examples in the book. Again, example 2.6 and 2.7. These are really good, and they both kind of lead into question 2 on the practice exam. And so that's all I'm really going to say about this, except for some kind of tips on question 2. So we have an exponential function there. Our velocity is given as some exponential function of t. Here, I just want to remind you, if we have an exponential function of x and we have to integrate it, we have to divide by the thing that multiplies by x. Now, in that problem, it's something like t over tau. So you have 1 over tau is your thing that multiplies the t. But so you'll have to think about how what I'm writing here relates to the problem. But you can do that. So anyway, if we integrate e to the x dx, we'll get 1 over a times e to the ax plus some integration constant. Now, the nice thing about integrals in physics is that we never have to worry about the integration constant because we're always working with definite integrals. In other words, they have limits. We always have limits of integration in physics. And so the integration constant actually drops out. And here's why. For example, if I have e to the at dt, and I'm integrating from t1 to t2, my integral, my antiderivative is 1 over a e to the at plus a constant, right? And then I'm going to evaluate that at t2 and t1, and I'm going to subtract. So when I do that, I put in my antiderivative, including the plus c, and then I subtract the same antiderivative, including the plus c, but I'm going to substitute in, the first time I'm substituting in the upper limit, and the second time I'm substituting in the lower limit. And then you can see when I subtract here, if I distribute out the negative sign here, I have plus c, and I'm going to get a minus c. The c is always going to cancel anytime you have a definite integral with limits. So that's why in physics, we don't worry about the constant of integration. Okay, that's been a long video, and that's the end of this topic.